Okay, good afternoon. So last time we started talking about relations, and we're going to continue talking about relations today. I left off last time giving a bunch of examples of relations that had different properties. So that some of them were reflexive, symmetric, antisymmetric, and transitive. So those are the properties that relations have. What I'd like to do next is start talking about some of the things that you can do with relations. And just like with sets and with propositional logic and so on, the way we work with these things is by combining them in some way. So what I'd like to talk about, at least for the beginning of today, is the idea of combining relations. So this is how we make new relations out of old relations. And if you remember the last class, I said that relations are really just sets, right? They're subsets of a Cartesian product of a set, possibly with another set or with itself. So everything we already know about how to combine sets also applies to combining relations. So relations are sets. So they can be combined the same way, or ways, that sets are. So what that means is you can take the union, you can take the intersection, you can take the difference of relations just like you can with sets. So let's do some examples, and hopefully this will be clear. So let's let A be the set 1, 2, 3, and B be the set 1, 2, 3, 4. And let's say we have some relations from A to B. So R1 is a relation from A to B, defined in the following way. R1 is 1, 1, 2, 2, and 3, 3. That's a perfectly good relation from A to B. And R2 is another relation from A to B, and it's defined in the following way. R2 consists of the pairs 1, 1, 1, 2, 1, 3, and 1, 4. So the question is, how can we combine these two relations? And we combine them in the same way we combine sets. So we might want to know, what is R1 union R2? What is R1 intersect R2? What is R1 minus R2? And we might want to do it in the other way, right? Because subtraction isn't commutative. You can't switch the order, but you can for union and intersection, right? Just like addition and multiplication are commutative, you can switch the order, but subtraction you can't. All right, so let's write out what these sets are. And remember, these sets are really just relations, but we don't have to think of them that way when we're taking their union and intersection and difference. So what's going to be in the set R1 union R2? Yeah?
1, 1.
Yeah, 1, 1 is going to be there. 2, 2 is going to be there. 3, 3 is going to be there because they're in R1. And now we write down what's in R2. Well, I already wrote down 1, 1, so I won't write it again. But there's 1, 2, 1, 3, and 1, 4. So that's the relation R1 union R2. It consists of all pairs that are either in R1 or in R2. So the intersection works similarly. So I look at all of the pairs that are in both. In this one, what's in common between R1 and R2?
1, 1.
Right, 1, 1 is the only thing that I have in both of those sets. So 1, 1 is in the intersection of those two relations. What about R1 minus R2? Right, I'm going to get 2, 2, and 3, 3. I don't keep 1, 1 because I have a 1, 1 in R2, so that goes away. And if I do this the other way, so R2 minus R1, what am I left with then? 1, 2, 1, 3, and 1, 4, exactly. So 1, 2, 1, 3, and 1, 4. All right, I don't keep 1, 1 because 1, 1 is also in R1. So that's how you combine relations. Questions about that so far? Okay, so if you understand how this works for sets, you should understand how this works as well. All right, so let's do something a little bit more complicated, where we don't have these explicit definitions. So let R1 be this relation AB such that A is less than B, and let R2 be the relation A comma B such that A is greater than B. And these are both over the set of real numbers. So these are two relations that are from the set of real numbers to the set of real numbers. So in that case, we just say over the set of real numbers. So I can ask the same questions I did before. So R1 union R2, R1 intersect R2, R1 minus R2, and R2 minus R1. What's R1 union R2? Not quite. So remember, I have pairs of real numbers here. So I'll do this in two steps. First, I'll write it out as sets. So it's all pairs AB such that A is less than B. Whoops. Union all pairs A and B such that A is greater than B. So that is the answer in some sense, but if I wanted to write this out a little bit more nicely, what's an equivalent set that's simpler to talk about? Yeah?
A is not equal to B.
Right, it's all pairs AB where A and B are different. So it's AB such that A does not equal B. Right? The only way A is not less than B and not greater than B is if it's equal to B. Does that make sense? All right, so let's do the next one. R1 intersect R2. So this is the set of all pairs AB such that A is less than B and A is greater than B. Yeah, that's the empty set. There are no pairs such that both of those things are true. So this tells us just like we can have an empty set, so too can we have an empty relation. And that sort of has to be the case, right? Because relations are just sets, and sets can be empty. So there is the idea of an empty relation, and that is the relation where nothing is related to anything else. That's perfectly fine to define as a relation. It's not terribly interesting, but it exists. All right. What about R1 minus R2?
Yeah. It would just be R1 again?
Yeah, this is just R1. Because R1 and R2 are disjoint. They have nothing in common. And when you subtract two disjoint sets, you don't lose anything from the original sets. You just keep it. And the exact same thing is true in the other direction. These sets are disjoint. These relations, I should say, are disjoint. Does that make sense? So you should be comfortable with the idea of me giving you two relations in this format and then giving a nice description of what the union of those relations is, or something like that. Okay, so if we think back and to last class, we said that relations are a lot like functions in some sense. Right? They're not as heavily restricted as functions, but they are kind of like functions. And one thing that we can do with functions is compose them. Right? We can say f follows g of x, which is f of g of x. Well, relations are enough like functions that composing relations make sense too. So we can also compose relations. This requires a little bit more detail than the other operations, which is why I'm doing this separately. So let's phrase it like this. Let R be a relation from a set A to a set B. And it could be that A equals B. That could happen. And if we're going to compose relations, we'll need two of them. So let S be a relation from a set B to a set C. And notice that it kind of has to be this way, right? F follows G of X, that's F of G of X. So the output of G has to be a valid input for F. Well, the same thing happens here. The second thing in the set R has to match the first thing, the second thing in the relation R has to match the first thing in the relation S. And we'll see why in a second once I define what it is. So the composite, or composition, I should say, of R and S is the relation consisting of a certain kind of ordered pair, consisting of ordered pairs A comma C, where A is in the set A and C is in the set C, and there exists an element B in B such that two things are true, such that AB is in R and BC is in S. So what does this look like? Well, we have this element A over here, and this lives in R. In A. So this is the set A. We have this other set B, and we have this other set C. So this is B, and this is C. I'll write this underneath just to give myself a little bit more room. And the claim is that, well, we have AB in R. So this is R. And we also have BC in S. So why don't we just have this shortcut that goes, whoops, I said C twice. This other one should be A. Why don't we have this shortcut that takes us directly from A to C? Right? That's exactly the same as the composition of functions. It's just now I'm talking about the composition of relations. But the idea is exactly the same. So you go from one set directly into the other set. We have a special name for this. We call it S follows R, just like we did for functions. Okay, and again, this is S follows R. S follows R means I'm doing S second, right? That's what it means to follow something. And I am doing S second, right? First I go from A to B, and then I go from B to C. So I do S first, I do R first and then S. So S follows R. R comes first. Is that okay? So this seems weird until we start doing some examples. So let's do that. So let's suppose we have R. Let's say we have a relation R from the set 1, 2, 3 to the set 1, 2, 3, 4, and a relation S from the set 1, 2, 3, 4 to the set 0, 1, 2. And we can define these relations in the following way. So let's say R is 1, 1, 1, 4, 2, 3, 3, 1, 3, 4. And let's say S is 1, 0, 2, 0, 3, 1, 3, 2, and 4, 1. Okay, these are our two relations, and I would like to compose those two relations. So I would want to know, what is S follows R? What is that? So this is trickier than with functions, because with functions, you usually have some formula for the function, so you just write it down, do some substitutions, a little simplification, and you can go home. For this, it's a little bit more work, because we don't have a formula for the relation. We have all of these pairs, so we need to do a little bit extra work. So there's a couple of ways to do this. What I like to do is, well, usually when I write down my ordered pairs, I do it in lexicographic order, so alphabetical order. I sort by the first thing first, and then I break ties by the second element of the pair. And I only do that so that I can be nicely organized when I do my work. Of course, it's just a set, and therefore it doesn't have any order to it. So I start with where I begin from. And where do I begin from? What's the set I start in here? R. So R is the relation I start with. What set do I start with? 1, 2, 3, right? It's S follows R, so R comes first, and R starts in 1, 2, 3. R takes 1, 2, 3 to 1, 2, 3, 4. So I start there, and if you think about what that is, the set 1, 2, 3, that appears as the first thing in R. Right? That's where my set 1, 2, 3 goes. So I like to start there and see where I can get. That's what I like to do. So I'm going to start with the first thing in R, 1, 1. So I have a 1, 1 here, and now I look in S for all of the things that start with 1. So in this case, that's just this one. So I have 1, 1 in R, 1, 0 in S. So what will I have in S follows R? 1, 0. Okay, so to be completely clear about that, in case you don't see it, what colors did I use so I can match? So this matches there, so I end up with 1, 0. So the middles match, so I end up with what's on the other side. Does everyone see how I get 1, 0 in my composition? All right, so now I move on and see if there's anything else I can do. So I'm still on 1, 1. Is there anything else in S that starts with 1? No, so I'm done with 1, 1. And I move on to 1, 4. Yeah?
Is there a reason there's not a 1, 2, or 1, 3, or is it just like...
No, this is just an example. So different relations would have different outcomes for sure. Okay, so now I start with 1, 4 in R. So now I'm over here. And I look for everything that starts with a 4 in S. So the only thing that starts with a 4 in S is 1, 4. So I have 1, 4, 4, 1. So what goes in S follows R? 1, 1. Good. All right. And nothing else starts with a 4, so I'm done for now. So I move on to the next thing in R, which is 2, 3. So it starts with 2 and ends with 3. So I'm going to look for all of the things that start with 3 in S. So the things that start with 3 in S are here. So I have 2, 3, and 3, 1. So I'll have 2, 1. And I have 2, 3, and 3, 2. So I'll have 2, 2. Does that make sense? Okay. So that's all that starts with 3, so I'm done with that. And now I'm at 3, 1, so I look for all of the ones in S that start with 1. There's only the 1. I have 3, 1, 1, 0, so I should have 3, 0 in my composition. There's nothing else that starts with 1, so I move on to the next thing, which is 3, 4. That ends with 4, so I look for everything that starts with 4 in S. There's only the last thing, 4, 1. So I have 3, 4, 4, 1, so I give myself 3, 1 in the composition. Okay? And now I'm done. Right? There's nothing left to do. I've exhausted all the possibilities for the starting element. So this is the composition S follows R. Any questions about how I did this? So composition is extremely useful for reasons we'll see in a bit. So it might not be obvious why you'd want to do this now, but it comes in handy later. Okay, so one special case of composition happens when you take the composition of a relation with itself. Now, are you always going to be able to compose a relation with itself? No. What's the only time where you can? Right. So you can't compose a relation that's from one set to a different set with itself. That only works if you compose a relation that's on a set to that same set. So you can compose a relation over a set A, and that's valid for any choice of A you like. So this only works when the relation is over a single set. But nonetheless, it's still interesting. So here's an example. The relation is AB such that A is a parent of B, and this is over the set of people. All right. So in this case, what is R follows R? Well, let's think about it for a second. R follows R is the set of ordered pairs AC such that there exists a person let's say B, such that two things are true, right? Such that AB is in R and BC is in R. Right? That's the definition of composition. So what does this mean? Well, this means that A is a parent of B, and this means that B is a parent of C. So what does this mean in terms of the relation between A and C? A is not a parent of C. A is the parent of C. Right? A is a parent of B, B is a parent of C, so A is a grandparent of C. So this is exactly the same as AC, such that A is a grandparent of C. So that's what that relation is, and that's why this is interesting, or one of the reasons why it's interesting. Now, of course, at this point, you can take the composition of R follows R with R. And if you did that, what would you end up with? Great-grandparent, exactly. So if you did this composition again, you could compose it again with R and get is a great-grandparent of. Okay? So because we do this so often, we have some shorthand for it. So we write r squared to be r follows r. Right? And then we would write r cubed to be r follows r follows r. That's not a union, that's a follows. Maybe it should be completely explicit. Okay? And then we keep going like this. So this is exactly the same as r squared follows r. Okay, so that's how we do it. Any questions about that shorthand? So let's see something here. Let's use this and see where we get. Suppose that R is the relation 1, 1, 2, 1, 3, 2, 4, 3 over the set 1, 2, 3, 4. And I want to see what happens when we start composing this relation with itself over and over again. So r to the 1 is just r, right? That's easy enough. R squared, well, that's just r follows r. And I would like to write out what it is that is. So let's do this same trick we did before. If you find it helpful, you can write it off to the side, another copy of what's going on. So let's do that over here, just for our reference. We have r is 1, 1, 1, 2, whoops, sorry, not 1, 2, 2, 1, 3, 2, 4, 3. And we want to compose it with itself. So 1, 1, 2, 1, 3, 2, 4, 3. Maybe you don't need to write it again. Maybe you can keep it straight, and that's totally fine. All right, so we're going to take the composition of these relations just like we did before. We already know how to do that. Don't let the fact that it's the same relation throw you off. You're doing exactly the same thing. So I start with 1, 1. And I look for all of the things in the other relation that start with 1. There's only 1, 1. So I have 1, 1, I have 1, 1, so I get 1, 1 in my answer. There's nothing else that starts with 1, so I move on to the next thing. 2, 1. What starts with 1 in the second relationship, well, just 1, 1. So I have 2, 1, I have 1, 1, so therefore I have 2, 1 in my output. That's nice. Nothing else starts with 1, so I move on to the next thing. 3, 2. So what starts with 2 in the relation? Well, just 2, 1. So I have 3, 2, I have 3, 1, therefore I have 3, 1. There's nothing else that starts with 2, so I move on to the next thing, 4, 3. What starts with 3? Just 3, 2. So I have 4, 3, 3, 2, so I have 4, 2. And that's it. So that's our square. Let's see what happens if we do this again. So r cubed, we know that r cubed is r squared follows r. And now you have to be very, very careful because it's easy to do this in the wrong order. So let's stop for a second and think about what we did last time. We'll go up here. We have S follows R. So the second thing is the top one. The first thing is the bottom one. Right? Because I have S follows R, and R is on top. Everyone agrees with that? All right. So, in this one, I have R squared follows R. So R should be on top. and r squared should be on the bottom. So r squared, I just copy from over there. It's 1, 1, 2, 1, 3, 1, 4, 2. So that's the most important thing, is getting that straight. It's very easy to make a mistake here and go from one set to the wrong one. Notice that if you think about what r squared follows r means, you also won't get that wrong. R squared follows r means you're doing r first, so r should be on top. Does that make sense? All right. So now we do the exact same operation to compose these. So I'll start here, 1, 1. The only thing that starts in r squared with 1 is 1, 1, so I get a 1, 1 here. Move on to the next one, 2, 1. Well, the only thing that starts with a 1 is 1, 1, so I still get a 2, 1 there. Move on to the next one, whoops, 3, 2. I have 3, 2 and 2, 1, therefore I'll get 3, 1. Still. And I move on to the last one. I have 4, 3, 3, 1, so I get 4, 1. Everyone sees that? All right. So that's R3. Let's do it again for R4. R4 is R cubed follows R. So I'll continue my little work off to the side here. I'll copy down R again. And I know that R goes on top. And remember, R doesn't change. And R cubed goes on the bottom. And R cubed is 1, 1, 2, 1, 3, 1, and 4, 1. So now I do this again. I have 1, 1 and 1, 1, so I get 1, 1. Move on to the next one. In general, you could have more than one. In this particular relation, we only have one. We have 2, 1 and 1, 1, so I have 2, 1. And now I move on to 3, 2. I have 3, 2 and 2, 1, so I get 3, 1. And I move to the last one, which is 4, 3. I have 4, 3 and 3, 1. So I get 4, 1. So what do we notice now? Yeah, R4 is exactly the same as R3. So no matter how many more compositions I take, I will always just have this exact same thing. So at this point, I'm stuck. So if I keep on going, R to the n is exactly equal to R to the 3 for all n at least 3. That's kind of neat. And I'm not going to prove it to you, but this will always happen, no matter what you do. Now the value of n for which this happens might be different, but eventually you'll always get into this situation. That's kind of neat. I'm not going to prove it, but we will use it throughout the course, so you can take that as a given. The value of n for which this happens, we'll talk about soon. All right. So one neat thing is you can actually understand transitivity, so the transitive property relations, in terms of this composition. Because if you look at what you do in a composition, well, you're sort of leaving out a middle thing somewhere, right? So when I had like 2, 1, 1, 1, and I just said 2, 1, or I guess that's not a great example. If I had 3, 2, and 2, 1, I could come up with 3, 1. Well, I'm sort of excluding the middle thing, and that's exactly what you do when you're talking about transitivity. So somehow the idea of being transitive and the idea of taking a composition, those seem like they're related, and in fact they are. So they're related in the following way. a relation R on a set A is transitive, if and only if, so this is a bidirectional thing, if and only if R to the n is a subset of R for n at least 1. So R is transitive if and only if R to the n is a subset of R for n at least 1. Is it clear what the claim is? So if you did all of these compositions, and there are infinitely many, right? N is some integer bigger than or equal to 1, so it's for all of those n's, then they're all a subset of the original relation. So you never add anything new. And that sort of makes sense at an intuitive level, hopefully, because when you take this composition, you're basically looking for these pairs where there's a middle thing missing. And if a middle thing is never missing, then it must be transitive. That's the intuition behind it, but I am going to prove it to you. So this is an if and only if proof, which means I really have to do two proofs. I need to prove that a relation R on a set A is transitive if R to the n is a subset of R for n at least 1, and I need to prove if R to the n is a subset of R for n at least 1, then R is transitive. So I need to go both ways. So I'm going to go backwards first. So to indicate that, I'm going to do a backwards arrow. So suppose R to the n is a subset of R for n at least 1. Right? That's what I'm starting with. And now I want to prove, I want to show that R is transitive. That's my goal. That's what I want to do. Okay, so if R to the n is a subset of R for n at least 1, then definitely R squared is a subset of R. Right? If R to the n is a subset of R for all n, then certainly R squared is a subset of R. This is existential instantiation. Okay. Universal instantiation. Okay, so what does that mean? If R squared is a subset of R, what does that mean? Okay, well let's start talking about what this means in terms of the set. Suppose that AB is in R and BC is in R. Right? Because this is the definition of transitivity. Remember, my goal is to prove that R is transitive. So the way I do that is I assume that I have AB and BC in R, and now I show that I also have AC in R. I'm proving that implication. So I assume that I have AB in R and BC in R, and now I would like to prove that AC is in R. Okay, so if I have AB in R and I have BC in R, what do I know about R squared? Right, so if I have AB in R and BC in R, I must have AC in R squared. Right, that's the definition of the composition. AC is going to be in the composition if AB is in R and BC is in R for some B. And the claim here is that it is. So that means AC must be in R squared, and that's almost what we want, right? We want to prove that R is transitive, so we've assumed that we have AB in R, and we've assumed that we have BC in R, and I'd like to finish the job by saying that AC is in R, and I'm close. I proved that AC was in R squared. So how do I finish this? So there's one fact that I know that I haven't used yet. Yep.
Because R squared is a
Yeah, since r squared is a subset of r, anything that's in r squared is also in r. So if I combine these two facts, then AC is in R. Right? AC is in R squared, and anything that's in R squared is also in R. Therefore, AC has to be in R. And that's exactly what I wanted to show, because now I've shown that if AB is in R and BC is in R, then for sure AC is in R. And I didn't say anything about what A, B, and C were. They could be anything. So therefore, R is transitive. That's tricky. Do people see and or believe that? Any questions? Okay. So let's go in the other direction now. Again, the first thing you want to do is write down what you're assuming. Okay? So we're going to assume that R is transitive. So suppose R is transitive, and we want to show that R to the n is a subset of R for n at least 1. Right? That's what we wanted to show. All right, so one thing you might notice is that for sure n is a positive integer, right? N is at least 1, and it has to be an integer. You can't take a fraction of a composition. So really, this is asking us to show that R to the n is a subset of R for all positive integers n. So what does this tell us that maybe we could try here? Not a summation. Yeah? Yeah, this feels like maybe we want to do induction, because for n at least 1 is the same as for all positive integers n, and that usually hints that we should try induction. So let's try a proof by induction and see how this goes. So we start with a basis step, and our basis step is going to be n equals 1. And I know it's n equals 1 because the statement says for n at least 1. So the smallest n can be is 1. All right. So if R is transitive, well, R to the n is just R to the 1, which is R. So this is really asking me to prove if R is transitive, then R is transitive. And that's definitely true. Right? I don't have to do anything there. The statement is, if R is transitive, then R is transitive. And that's obviously correct. Okay, so that's kind of nice. The basis step is out of the way. So now we do our inductive hypothesis. Our inductive hypothesis is that we assume R to the k is a subset of R for some arbitrary k. And in the inductive step, I want to show that R to the k plus 1 is a subset of R. That's what I would like to show. Is it clear what I've done here? All right. So what we'd like to show is that R to the k plus 1 is a subset of R. So typically the way you do that is you say, okay, suppose we have something in R to the k plus 1. I want to show that it's also in R. And if I can do that, well, what I'm doing is I'm proving that if x is in r to the k plus 1, then x is in r. And if x is arbitrary, that must mean that r to the k plus 1 is a subset of r. Right? This is the exact trick I described when I was talking about sets and subsets and asking you how to prove that a set is a subset of another. So that's what we'll do. Okay? So suppose that AB is in r to the k plus 1. And this is for some A and B. Okay, I don't know anything about them. They could be anything at all. And my goal is to prove that AB is also in R. That would make me happy because then I would be done. All right, so let's try to do that. Let's think about what it means for AB to be in r to the k plus 1. So we know that AB is in r to the k plus 1, and we know that r to the k plus 1 is r to the k follows r. Right? That's the definition of what that means. So let's zoom in on that second thing for a second. If r to the k plus 1 is r to the k follows r, then there must exist some x such that the following is true. Ax is in r and xb is in r to the k. All right, that's what it means to be in r to the k plus 1. Does everyone see that? All right. So, we're getting close. We don't really want to know about r to the k, though. Right? Remember, I'm trying to prove that AB is in R, and I don't really care about this r to the k. So I need to get rid of that r to the k somehow. So who sees a way I can get rid of that r to the k? So what do I know? Yep. Right, I know by my inductive hypothesis that r to the k is a subset of r. So if xb is in r to the k, then xb also has to be in r. And this is by my inductive hypothesis. Okay, so this is kind of nice. Now I have that ax is in r, and I have that xb is in r. So if I combine these two facts, what does that tell me? Okay, how do you know? So maybe we forgot. This whole thing started with assuming that r was transitive. So we know r is transitive, and we know that ax is in r, and we know that xb is in r. Therefore, you're right, AB has to be in r. And this is because r is transitive. And now we're really happy because what we've shown is that AB is in r, and what we wanted to show was that AB was in r. So we started by assuming that AB was in r to the k plus 1, and now we've shown that AB is also in r. So that must mean that r to the k plus 1 is a subset of r. So therefore, r to the k plus 1 is a subset of r, which means our proof by induction is over. So let's go back up and look at what the statement of what we just proved is, because it's easy to forget. So a relation R on a set A is transitive if and only if R to the n is a subset of R for n at least 1. This sounds like almost more work, right? To check to see if R is transitive, what you can do is you can take infinitely many compositions and check to see if they're all subsets of R. That's not a shortcut. That's doing an infinite amount of work. So that's not good. But we already know from the previous example that eventually this stops. Right? If you keep composing a relation with itself, eventually you'll get stuck in one relation, and that relation will just keep on coming up over and over again. So when I say that you have to do infinitely many compositions to check to see if it's transitive, you don't really, because after some finite number of compositions, they're all going to be the same, so the answer will always be the same from that point on. So in this example, up here, if I wanted to check to see if R is transitive, I really just need to compute R to the 1, which is easy, it's just R squared, and R cubed. Because after that point, everything is equal to R cubed anyway. So then I just check, is R a subset of R? Yes, obviously. Is R squared a subset of R? Well, that's a good question. 1, 1 is there. 2, 1 is there. 3, 1 is not there. So this thing isn't transitive, and we're done. Right? That's one way to check it. Yeah?
Is there like a way of telling how long it will take a set like this to start repeating forever? Because a really, really big set might take a really long time.
Yes. So the way you tell, and so I can't give you an exact number for a lower bound, but I can say what it is at most. So what's the largest amount of compositions you could take before this will work? Well, what's the largest number of middle elements you could have to go through? Any ideas? So this particular relation is on a set of size 4. Yeah? It's not even that much. It's just the number of elements that you have. So in a set of size 4, you're guaranteed that this process will end by the time you take 4 compositions. So if you had a set of size 100, or a relation over a set of size 100, I should say. So to be clear, the thing I'm counting here is this size, the number of elements. I'm not counting this size. There does happen to be 4 in both, but that's not what I'm counting. I'm counting the size of the set. So if you had a relation over 100 elements, the composition would converge in some sense by 100 compositions, but it could be a lot sooner. So in this one, our guarantee was that it would happen within 4, but it happened within 3. Okay? So this n here, really, n could be anything, but because we know that this stops after a while, this n is really the size of the set that the relation is over. Okay, I haven't shown that to you yet. You just have to take that on faith for the time being, but that is the case. Any questions about this? So this is really tricky, right? This combines like everything we've learned in this class. You need to know a lot about relations. It's a proof by induction. There's some direct proofs in there. There's tons of material here. So if you fully understand this proof, you're probably in pretty good shape for most of the stuff we've covered. All right. So the next thing I'd like to talk about is to go back to this reflexive, symmetric, and transitive stuff. And sometimes when you're working with relations, you're doing it in some particular application. Like maybe you're working with a database or something like that. And for whatever reason, maybe your relation is not transitive, or maybe it's not reflexive, or not symmetric, but you'd like it to be. So let's say maybe you're working with some database, and there's this relation is related to, where related to means there's some bloodline connection, right? So maybe some distant relative. And you'd like to work on this database, but you notice that, this relation is related to, it should really be symmetric, right? If I'm related to someone, then they should be related to me, for sure. So conceptually, that relation should be symmetric, but sometimes data gets messed up and weird things happen, and for whatever reason, the relation is not symmetric. So what we would do in a case like that is we compute something called the symmetric closure of the relation, and that's the smallest relation that is a superset of the original relation, but is now symmetric. So you can think of it as adding as few elements as possible to guarantee that it's symmetric. And the same thing you could ask for the reflexive closure. That's adding as few elements as possible to guarantee that it's reflexive. And for the transitive closure, that's adding as few elements as possible to guarantee that it's transitive. And we want to do this so that the relation looks as close to the original relation as it can, but it has these properties. So that's the idea of a closure of a relation. So I'm going to start with the easy one, and that's the reflexive closure. As you might imagine, it's not too much work to guarantee that a relation is reflexive. So sometimes, as I said, a relation does not have some property that we would like it to. So for example, reflexivity, symmetry, and transitivity. We don't really think about the anti-symmetric closure because to make a relation that's not anti-symmetric symmetric, not anti-symmetric become anti-symmetric, you have to remove elements from it. And we don't usually like to lose data, we prefer to gain data. So that's why I'm not going to cover an anti-symmetric closure. But I will cover the reflexive, symmetric, and transitive closures. So the question is, how do we add elements to guarantee these properties? And you might say, oh, that's really easy. My relation is a subset of A cross B. So if I just take the union of my relation with A cross B, then I'll certainly be reflexive, symmetric, and transitive. And yes, that's true, but you also lose all of your data, right? It sort of gets lost. So that's maybe not so nice. So we'd like to refine that a little bit and do it in such a way that we add as few new elements as possible. And we do this to preserve the meaning of the original relation. That's the idea. So is it clear what I'm trying to do when I say take the reflexive closure, for example? So maybe it's missing 1, 1, so I add 1, 1 back in. The reflexive one is easy, as we'll see in a second. So first, let's consider making a relation reflexive. So suppose R, so I'll write it out. So suppose we have a relation R on a set A, and we want to make it reflexive. So what that means is we need to ensure that A comma A is in the relation for all A in A. And you don't want to add anything else. All right. So the way we do that is the following. We define something called delta. So that's a capital delta, which looks like a triangle. And it's the following special set. It's A comma A such that A is in A. So it's all of the matching pairs, if you like. The reflexive closure of R is just R union delta. That's it. So that's all the reflexive closure is. So all of those elements in delta have to be there. So for example, if A is 1, 2, 3, then delta is 1, 1, 2, 2, 3, 3. And all of those elements need to be there, and nothing else does to make it reflexive. So I just add in those elements. And of course, this is a union, so if they're already there, they don't go away or anything like that. Okay, so let's do an example. Let's say R is A comma B such that A is less than B, and this is over the set of integers. In this case, what is delta? Well, it's AA such that A is in Z. There's another way that you could write that, though. What's another way you could write this? Maybe is A comma B. Yeah, it's all AB such that A equals B. And now if I take R union delta, well, that's A comma B such that A is less than B, union A comma B such that A equals B. And what's that? Yeah, it's AB such that A is less than or equal to B. So the reflexive closure of the less than relation is the less than or equal to relation. Does that make sense? Okay, if this makes closures seem easy, don't worry, it gets more interesting. So that's the reflexive closure. I'd like to move on to the symmetric closure next. So the symmetric closure. Well, for the symmetric enclosure, we want to ensure that BA is in the closure whenever AB is in the original relation. That's what we'd like to do. And we do a very similar thing to the reflexive closure example, but I define something slightly different. I'm going to define R inverse, so R to the minus 1, to be equal to B comma A such that A comma B is in R. So this is the inverse of a relation, if you like. All of the first things in the pairs become second things, all the second things become first things, within the single pairs. Okay, and then the symmetric closure is just R union R inverse. So the symmetric closure of R is R union R inverse. And notice again, we're not adding any elements that don't have to be there. Right? All of these elements have to be there, so nothing extra is going to happen. And we can't add any less because all those elements really do have to be there. Yeah?
If you take R follows R inverse, do you get some weird R to the 0 thing?
Yeah, that's a good question. So what happens if you do R follows R inverse? Does anyone have any thoughts? AA? Okay, well let's try it and see what happens. So let's say R is, I don't know, let's do one of the examples I had earlier just for the sake of consistency. Let's do this one. Okay, so if we have that, what is R inverse? Well, 1, 1 gets switched, 1, 2 gets switched, 2, 3 gets switched, and 3, 4 gets switched. All right, let's do R inverse follows R. And then maybe, if we think it matters, we'll do it the other way. So I have 1, 1 on top, 1, 1 on the bottom, so I get 1, 1 here. Oops, 1, 1. I have 2, 1 on top. I have 1, 1 here, so I get 2, 1. I have 2, 1 on top, 1, 2 on the bottom, so I get 2, 2. And I have nothing else that starts with 1. So I move to the next one. Oh, I left out 1, 2, sorry. I go to the next one, which is 3, 2. I have 3, 2, 2, 3. So I get 3, 3, and nothing else. And I go to the last one, 4, 3. I have 3, 4, so I get 4, 4. So that's not nothing, and it's not everything. It does have one property. It is going to be symmetric, and it's also going to be reflexive. So you don't get anything particularly interesting in this case. But that's a good question. All right. So, going back to the symmetric closure, let's do an example. Let's do R is equal to A comma B such that A is less than B. So in this case, R inverse is going to be, well, it's going to be BA such that A is less than B. But I don't really like that. I prefer to think of it as AB such that what? Yeah, A is greater than B is how I would probably phrase it. It's not wrong to phrase it the other way, but I find this a bit more natural. Okay, and then the symmetric closure of R is just R union R inverse. And what is the union of these two things? We've already done it. A does not equal B. So the symmetric closure of the less than relation is the not equal to relation, which is maybe kind of interesting. All right, so the last one we'll do is the transitive closure. And if you think this is easy based on the last two, you'll see fairly quickly that the transitive closure is not easy. So let's try it. Let's say R is equal to 1, 3, 1, 4, 2, 1, and 3, 2. And this is on the set 1, 2, 3, 4. And this is not a transitive relation. So who can see why it's not transitive? Yep. No force something. So that's okay. I mean, it's only going to violate transitivity if I had 1, 4 here, then 4 something, and then I didn't have 1 and then the other side of it. Yeah? Okay, so, whoops. So 1, 2 is missing. Is there anything else missing? Yeah? 2, 3 is missing. Right, because we have 2, 1, 1, 3, but there's no 2, 3. Is there anything else missing? 3, 1. So where would we get 3, 1? Right, so 3, 1 needs to be there, but it's not. Anything else? There's one more. Yeah? 2, 4. So 2, 4 is missing, and that comes from 2, 1, 1, 4. So those are the 4 things that are missing from this, this relation. So the natural thing to do would be to try adding them in and hoping for the best. So let's say, let R prime be 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 3, 1, whoops, I left it 2, 4, 2, 4, and then 3, 1, 3, 2. So I'm just doing these in lexicographic order to make it look nice and be easier to work with. So what I did is I took the 4 original things I had and then added in the things I felt were missing. So those were 1, 2, 2, 3, 3, 1, and 2, 4. And then 4 remaining things are from my original set. All right. So at this point, we would kind of hope that maybe this thing is transitive, because we added in all of the things that were missing. So is this thing transitive? Yeah? Right. This thing does not have 3, 4, but it needs 3, 4. So why does it need 3, 4? Well, it has 3, 2, and 2, 4. So it has 3, 2, it has 2, 4, but it doesn't have 3, 4. And therefore, this is not transitive. So it seems like we'll have to do a little bit more work here. And it seems like we need to do something else. And to figure out what it is that we need to do, we go back to this idea of composition, right? Because we remind ourselves that composition and transitivity are somehow very linked. So remember that if we compose R with itself, then we get all of the elements where a middle thing has been skipped, right? Where the middle thing is now hidden. And you need to have those elements for transitivity. They have to be there. Right, so all of those elements in R squared need to be there. So you have to add them. And that's exactly what we did here. Essentially, we just computed R squared and added those elements. But this example shows that that, unfortunately, might not be enough. But if we go back to some of the results we've already seen, like up here, a relation R on a set A is transitive if and only if R to the n is a subset of R. So what if we went ahead and started computing these compositions and took the union of all of them and added them to my set, to R? Well, if I did that, I would get something transitive, which is nice. And in some sense, it's the smallest transitive thing I can have. So I'll show you how to do that next time. But before we go, I'd like to talk a little bit about some housekeeping stuff. So, in case you've forgotten, our test is next week. It's our 3rd and final test. The sample test has been posted since Tuesday evening. I strongly encourage you to go over it. Make sure you can do it. You should believe me by now that these sample tests have a lot of overlap with the real test, and this is no exception. So please go over it and do it. The very last thing is that your assignment is due tomorrow. Your fourth and final assignment will come out sometime tomorrow evening after the due date and after the solutions for this one goes up. I say it every time, but people don't believe me. I do not take late assignments. The assignment's due at 4. After 4, you will not be able to submit. All right, that's it for today.